The bridge circuit is one of the most popular circuits that is used for driving loads through PWM signals, through pulse width modulation signals. So let me draw this bridge circuit. This is one half the bridge, and I am using the MOSFET symbol here. MOSFET, this is a N-channel MOSFET with an internal body diode. There's another N-channel MOSFET with an internal body diode. So this forms one part of the bridge. The other part of the bridge, I'm going to have again MOSFETs here, and then later draw the internal body diodes like this. So this forms a bridge circuit. Now in between here is where I'm going to connect the load. So the load can be any load. It could be an RL load, can be an RC load, can be a motor load. So that will get connected in between the bridge here. So let's say this is Q1, this is Q2, Q3 and Q4, and we have VCC here as the DC link voltage. Now this is the full bridge circuit, and by switching the different MOSFETs, we can get pulse width modulation here. Almost majority of the loads will be switched using full bridge circuit topology, and by the pulse width modulation strategy that we discussed previously. Now let us say that we would like to get sinusoidal voltage fundamental across this, which means that you will get pulse width modulated signal here, but when you filter it out and remove the fundamental, it should have a sinusoidal wave shape, which means that a sinusoidal wave shape is modulating the high frequency triangular carrier to give you the PWM signals, which is going to switch these MOSFETs. So let us see how we are going to give the pulses. So we know that we can give a sine wave as the modulating signal, compare it with a triangular wave and get a PWM signal. Let me draw that for you here. So I am having the y-axis and the time axis here, and the y-axis will give you the signal amplitudes. So let me take a sinusoidal profile like this. Okay. And the modulation pattern, so you will see that the modulation pulse width will be lower here because the amplitude of the signal is less, and then the modulation width will be larger towards the center of the sine wave where the pulse amplitude is higher, and then actually gets lower, and once it starts getting a negative maximum, you will see that the pulse amplitude will be maximum on the negative side. So let me draw this for you so that you get an idea. So you see that the pulse widths are smaller here, than the pulse width is large near the peak. I am taking a carrier frequency which is not too high compared to the modulation signal, so that I can see the pulse pattern. But in a practical sense, the frequency of the triangular carrier will be much higher compared to the modulating signal, and then you will see a band. But I want you to see the edges moving up and down. That is why I am taking a lower triangular frequency. And then likewise you also draw for the negative part, so where you will see the negative part pulse width is larger here, goes like that. Then I'm copying this one and then pushing it to this side. So now if I have to get a pulse width modulated waveform here with a sine contained in the fundamental, then let us say I have this sinusoidal pulse width modulated waveform given here. On this side, with the same triangular carrier, I will give not, if I give a pattern like this, what will happen? This minus this, you will end up with 0 fundamental. Now what I will do, for this part of the bridge, I will compare in this fashion. I will, for the same triangular carrier, I will use an inverted sign. Whatever the sign signal, I will pass it through an inverter and use the inverted sign to compare with that same carrier, and I will get a pattern something like this. Now if I subtract this minus this, you will get a fundamental which is a pure sine wave of double the amplitude. So this way I can generate a sinusoidal pattern across the load which is connected to the centrum of the bridge. But how do I switch these? So now look at this. So when this is negative, which means that this has to be, this implies that which implies that this should be low. So which means this is switched on, this is switched on. So when you say that this is switched on and this is switched on, you will see that this is positive on this side, negative on this side. So you will have overall a pulse width modulation pattern coming in that fashion. And then this goes positive, this goes negative. So this would go positive, this will switch off, this will switch off, and this will turn on. So you will have connection to VCC in this fashion. So you will see this is positive and this is negative. Then during this portion, you will see that I need to connect Q1 to this one, Q2 is off, and Q4 is connected here, so that you get a pattern where this is more positive than this. So like that, you can see that these two are mutually exclusive. Q1 and Q2 are mutually exclusive. Q3 and Q4 are mutually exclusive. You cannot have both of them conducting together. Q1 and Q2 cannot conduct together. Q3 and Q4 cannot conduct together. They have to be mutually exclusive in time. However, there is a slight problem due to non-idealities. When I am, let us say for example, Q1 is on, Q2 is off. Now at some transition here, Q2 has to turn on, Q1 has to turn off. So this has to move from on to off, and this will move from off to on. And it is not going to happen at 0 time. There is going to be a finite time of transition, which means this will move through the linear region to off position. This will also move through the linear region to on position. So during the transition time, there is a very small period of time where there can be a shoot through, means there is a current that can flow from VCC down to the ground through the Q1, which is transiting through the linear region, Q2, which is again also transiting through the linear region, which means that there are finite conductivities. So this shoot through can be pretty large because VCC is only impeded by the impedances offered by the device which is undergoing transition, Q1 and Q2. And this uncontrolled high current can lead to destruction of the device, and that is the reason that we don't want such a thing to happen. So let me just demonstrate this with a zoomed portion of this one. So let me zoom this portion, okay, and show you. So let me take one transition. You see that here the waveform is going from high to low. So let me take that transition and let me zoom it. Let us zoom it and see the voltage waveform across Q1 and voltage waveform across Q2, because top bottom transistors, that's what is important right now. And the same behavior will apply to the other arm also. So let me make some space here. So let me draw two axes, time axis. One I will call VCE Q1. The voltage across Q1 VCE. This is the collector emitter. It is a drain and source in the case of MOSFET, but I am using collector emitter in a very general sense, because this switch can be a BJT where you are talking of collector emitter and the base. It could be an IGBT, you are talking of collector emitter and the base, or it could be a MOSFET, drain, source, gate. Okay, so that's what I mean by VCE here. It means that the collector emitter or the drain source voltage of Q1 and collector emitter or the drain source voltage of the power semiconductor switch connected for Q2. Okay, so let us see what happens. So during just before this moment, Q1 was on, because this is high, Q1 must have been on, so that VCC is passed on to this point, and Q2 must have been off. So Q1 is on means that the voltage across that will be low or zero. So that's what I have drawn here. And now we are initiating at this point that Q1 should go off, which means that it should start withstanding a voltage. It should go off and then go from a short circuit zero voltage condition to a high voltage condition. So eventually you will see that it gradually rises, goes through the linear region and starts supporting voltage, which means it is in the off condition. What's happening to Q2? At this point, up to this point, Q2 had been off, which means it is supporting high voltage. So let me indicate it with these timelines. So let's say that Q2 is now supporting high voltage across its drain source or collector emitter. And at this point, I'm initiating turn on of Q2, which means that the voltage across this will gradually fall to zero. So the voltage across this will gradually fall to zero. So this is the turn on of Q2. This is turn off of Q1, this is turn on of Q2. But you see that when Q1 is in the on condition and Q2 is the off condition, there is no overlap, there is no shoot through. Here also Q1 is in the off condition, Q2 is in the on condition, there is no possibility of a current going from VCC to ground directly, no shoot through. But here this is passing through the linear, there is a finite impedance, this is passing through its linear region, there is a finite impedance, there can be a shoot through directly from VCC to ground and you will see a large current flowing through this. And this is the time region, though it may be in the order of nanoseconds. This time region is the danger zone where large currents, if the voltage is high, large currents could flow through it and blow up your devices. So what is required? So let me write this on the, let me repeat this slightly, indicating slightly to the right, so indicating the requirement. So this time is called the transition time, and I don't want a time, any time where there is a finite impedance from VCC to ground. So let me draw the requirement on the right side. Again, I am taking two axes. One axis for the collector emitter of Q1 or the drain source of Q1, and the collector emitter of Q2 or the drain source of Q2, depending upon which semiconductor switch you are using. So let me mark that. So let me first draw Q1. Q1 was on. So this is exactly like this. Q1 is on, and at this point I am initiating turn off of Q1. So how does it go? It goes on this fashion. Now comes the difference. I initiate the turn on of Q2 after some delay. So I allow Q2 to be off up to this point when I know that fully Q1 has turned off, and then only I will initiate turn on, and it will go through its finite impedance zone and then goes to the on state. So if you see here, at any time, here you will see that this is the off condition, this continues to be in the off condition, so there is no shoot through. And at this point, I am sure that this is in the off condition and therefore there cannot be a shoot through, this is turning on. So there is no time when both are in transition, and there is no time when VCC to ground there is a finite impedance where there can be a large shoot through. So therefore, when I mark the time here, indicate this time, this is the time where I initiate turn off of Q1. Initiate Q1 turn off at this point. Then I wait for some time and then I initiate here turn on of Q2. So this delay is called the dead time. So I have to consciously give this dead time in the PWM signal if between the top PWM and the bottom PWM, so that I do not have shoot through. So how do we derive the gate signals for the top switch Q1 and the bottom switch Q2, and so on similarly for Q3 and Q4. Now that's what we will discuss, and we will also try to incorporate a delay circuit where you will see this delay come into the picture, incorporating dead time and avoiding direct shoot through currents. In the literature, you will see that I will clip this, take only the positive signals and then give that to the gate drive of Q1, and I will invert that and give that one to the gate drive of Q2. That's how the literature will show in the circuit diagrams. That will not be a practical solution because of the shoot through problems. You have to give a conscious dead time. So I will introduce in between a dead time circuit, and that we will discuss how to do that. Let me start with the PWM signal, and from here let us see how we will generate the drive signals, gate drive signals for the top MOSFET and the bottom MOSFET in the case of a PWM modulated bridge circuit. So the PWM signal, if you take the top part, which I am shading here with green color, these are the parts that form the PWM signal, let's say for the top part of the half bridge arm for the top switch. Now if you see how do I get this waveform, you can either clip it or you can clamp it. But you see that you already had an op amp generating the PWM. The last stage, the triangle and the modulating signal were compared, and the output of that is a comparator which gives you the PWM output. So we could start from that stage. So let me bring that in. Let me copy paste it. So if you look at here and here, we give the modulating signal here M, Vm, and the triangle signal here, the VTRI, which is the triangular carrier, high frequency triangular carrier. When these two are compared, out comes the PWM waveform, and this PWM waveform is this blue colored waveform which you see, which goes both plus and minus, plus VCC to minus VEE. So let me remove this and make some space, and I will put a clamper circuit consisting of a resistor and a diode, and this is connected to ground, and I will put a Schottky diode. So I will use the symbol of a Schottky diode because the drop across the Schottky diode is around 0.1 to 0.2 volts, and the dynamics is also much faster than any other diode. It's the fastest in terms of dynamics, turn on turn off dynamics. So now if you see the waveforms with respect to this circuit, so this part, the blue part, which is going plus and minus, the PWM waveform generated from the comparator output is at this point here. Then after passing through the clamper, whenever this is positive, the diode is reverse biased and it goes through. The positive parts will go through. Whenever this goes negative, the diode is forward biased because this will be more positive, because when the output is negative, you will see that this is more positive than this, and then the diode will turn on and clamp the output to 0, and then there will be a current flow through this op-amp. So op-amp will be sinking current at that point in time and sink into minus VEE. So the waveform here will be the shaded green portion parts. So this will be the clamped waveform. You could also use a diode clipper and then get similar output at the output, only the positive part of the output. So next, let me redraw the half bridge top and bottom MOSFET. So you have the top MOSFET here, and the top MOSFET, the gate is given to a gate drive circuit. Just indicate this gate drive circuit. We have discussed the gate drive circuit in detail, and you will use one of the gate drive circuits to drive the MOSFET, the top MOSFET. And likewise the bottom MOSFET, this is connected to VCC, this is grounded. Do not forget to write the internal body diode for the MOSFET. Then you have the gate drive circuit. So you have the gate drive circuit here. Now this gate drive circuit, I am going to connect directly this part to the gate drive circuit. This is the green part. And what you want to connect here? So this MOSFET should come on during mutually exclusive intervals of time, that is during the time when the top MOSFET is off, you want to have the bottom MOSFET on, that is during all these blank zones or inverted portions, you will see the bottom MOSFET coming on. So basically, if you see, green inverted portion is the orange part. So we can put an inverter and then give it to the gate drive of the bottom. So let me do some naming. I'll call this as V top, I'll call this as V bottom, and this as PWM. So let us look at requirement. What is it that we require in terms of dead time and in terms of a dead time circuit, and where should this dead time circuit come and what should be the dead time circuit? So let me have this axis, time axis. X-axis is the time axis, and I am going to draw a zoomed portion of the PWM waveform here, the green one. So I will draw it like that, just a couple of pulses so that I see at least two transitions. I will call that one as PWM. So let me extend the time and have one more time axis. So now let me talk of V top and V bottom. We say this is Q1, Q2. During this time, Q1 is supposed to be on. During this time, Q1 is supposed to be off. Q2 is supposed to be on. And during this time, Q2 is off and Q1 is again on. Okay, keep that in mind for this two top and bottom. So during this time when Q1 is supposed to be on, V top is supposed to follow this. So let me draw V top. Is supposed to follow that. So it will be same as the PWM waveform which is seen here. V bottom is the inverted value of PWM. So we will do that one, V bottom. So it is the inverted value of PWM, and this is what you get, and see that during this time V bottom is high, which will drive Q2 on. Now here still the transition time issue is, transition is not taken into account, is not addressed. That problem is still there that we discussed, that during transition there is going to be a common finite impedance from VCC to ground, which will result in a very large shoot through current. We want to avoid. So therefore we need to give a dead time. So let me call this one as VG1. Call this one as VG1, gate signal, gate 1 signal, VG2, gate 2 signal. So how should gate 1 and gate 2 be? What is the requirement? So the requirement is as follows. So first VG1. So let me draw this VG1. This is the top MOSFET which is supposed to follow V top. And when the V top is turning on, the when V top is going low, turn off of Q1 is happening. So turn off of Q1 is being initiated along this line, and I will maintain that. So I will maintain that. Turn offs I will maintain. And here actually if you look at V top, Q1 is being turned on. So I will delay the turn ons of MOSFETs. So here I will not turn on at this point, even though turn on is initiated at this point from the original gate drive signal which is coming here. I will delay it and then initiate the turn on of Q1. So I will give a delayed turn on. Likewise for VG2, here what I am supposed to do is, okay, V bottom is the input signal for the gate drive. So we should see that again, turn on. Q1 is getting turn on, but turn ons I am saying that I will delay the turn ons of MOSFETs. So I will delay it and then turn on, but I am not going to delay the turn off. Turn off is getting initiated here for Q2 and I will maintain that. So you see now between VG1 and VG2 there is no common transition time. There is a delay between the turn off and the turn ons of the two gate signals, and this time difference is called the dead time. This delay time is called the dead time, which basically is the difference in the turn off initiation to the turn on initiation of the complementary MOSFET. So this we have to obtain. This we have to obtain by some circuitry. So where will that circuitry come? Just before the gate drive circuitry, here I want to insert this red shaded pre-block. So this pre-block is the dead time circuit block, and we will draw the circuit for generating the dead time such that we get at VG1 and VG2 waveforms like this, starting from this PWM waveform, here. Let us now draw the circuit for this part here, the dead time generation circuit. So let me make some space here, and I will use two AND gates to explain this concept. So the first AND gate is the one which is connected to the VTOP waveform, that is, which is connected here. Okay, I'm talking of this part of the block that I'm going to zoom out and draw, zoom in and draw. So VTOP is connected here, and it's connected to the input of AND gate. Both the inputs are shorted, and this is used only as a buffer. But because this is coming from an analog circuit, I want to pass it through a Schmitt trigger so that you don't have any metastable conditions. Then the output of this AND gate, I am going to pass through an RC filter, a simple RC filter, and the output of that is again going to another AND gate. So because this is also an analog input given to the AND gate, I have to remember to use Schmitt AND gates for these two. Then the second input, I am going to bring it from here. So I am going to bring the second input here. So remember that the AND gates are Schmitt AND gates. So the symbol here implies Schmitt AND gate, which can interface analog signals to the digital output. This also will be a Schmitt AND gate. So let us draw that. So the output of that is connected to a gate drive, and the output of that is connected to the gate of the MOSFET. So here in this case it is the gate of the top MOSFET. I am drawing this top MOSFET like this here. So this is basically this part. Gate drive and the MOSFET part is written again here so that for clarity. So this is the pre-circuit which you need to, or the pre-gate drive circuit that needs to be written to provide the dead time delays. Now the same thing I have to duplicate for the bottom MOSFET also. So let me push this and then let me duplicate that, and then I will place it here. So I will change this V top to V bottom. V bottom. So now we have the circuit for both the top and the bottom. This is VCC and this is ground. So let me mark some letters to identify the node points. This is A, and this is B, this is C, and this is D. This is VG1 and this is VG2. So now let us draw the waveforms at the various node points, and let us see if we get what we wanted, the dead time. So let me have some space here for plotting the waveforms. Let me have this time divisions. Okay, let me start from V top and V bottom. So V top first. So let me take V top. So, and then VA and then VC. VC I am writing it in red so that, okay, this is the important waveform. This will be same as VG1. VG1 with enhanced gate drive power. And then V bottom and VB and then VD in red. So these two will give you the waveforms of VG1 and VG2. So let us draw this V top. So V top goes like this, just like we saw here, V top, which is coming from here, right? So that is V top. And what is VA? So VA is, so the same V top waveform will get to this point, and then it is RC filtered. So there will be a RC filtered waveform at VA. So with first order filtering, you will see that. So let me draw this filtered waveform with this RC filtering, first order filtering. So this would how VA would look like with filter. And what is VC? So VA and this V top are given to the Schmidt and. The Schmidt and will have a trip point. So let us say the trip point is somewhere. Okay, before that I also want to share with you this falling. This falling is also happening, whatever the capacitor is charged during this time, this has to discharge when this goes low. This has to discharge like this. You can speed up the discharge if I put a diode here. So I can pass it through the diode and into this AND gate, provided the sink current capability of the AND gate is available. So I can put a diode like this so that capacitor has a quick path for discharge. Same here also. So capacitance should have a quick path for discharge. So this will take care of this falling. Actually, you don't need to be actually worried about this falling, because as you see from the waveform, this will be dominating for this. But you need to discharge this C as quickly as possible so that it is back into action for the next cycle. If the duty cycle is small or large, you need to have the capacitor back in action as quickly as possible. So that will decide the minimum duty cycle. Now coming to this AND gate, which has a trip point. So let's say this is the trip point. And let me draw the timeline down for VC. So up to this trip point, all these values are considered low. So which means the output C is low. V top is high. So this is enabled. This input of the AND gate is enabled. So once this crosses the trip point, this is high, this is also asserted high, and output will go high. So you will see VC will go high at this point. And then during the transition from high to low, this may take time to fall, but your V top is coming down immediately. So therefore you will see that this immediately transits to the low position. Then again here the trip point will cause the delay, and you will see the output going in this fashion. So this is VC. So notice this on time delay. There is a turn on. This is when the turn on, there is a turn on delay. Initiate the turn on with the delay. There is no change in the turn off. There is no change in delay for the turn off. Only the turn on is delayed. So V bottom is nothing but the inversion of V top. This is V bottom. Here again you will see VB is the result of a low pass effect of the RC filter, and it will be something like this. Here again this discharge time constant can be reduced by passing it through this diode, by placing a diode there. Now let's say the trip point for this turn on part is here for the Schmidt, and if I bring down the time projection, the VD will go high when both this crosses the trip point and this is also high. So the output here, VD, will go high only when V bottom is high and also VB point has gone beyond the trip point. So if you look at this will go high here where both this and this are high, and falling down is immediately as V bottom goes low. Immediately as V bottom goes low, VD will go low irrespective of the value of VB, and therefore we get a waveform like this. So look at VD and VC. So this VC and VD are the ones which have this delay, turn on delay, and as a consequence you see that there is no transition overlap, and then there is a dead time that is inbuilt, and we can adjust the value of this dead time by adjusting the RC parameters. So dead time for any given circuit can be adjusted by adjusting these RC parameters, and then you can fix the dead time and have it prefixing this gate drive circuit. So you see that VG1, VG2, what is required, our requirement is kind of met by this VC and VD, and VC and VD will flow through the gate drive, get enhanced in current, there will be a current amplification and appear as VG and VG1 and VG2 with having the same wave shape, similar kind of wave shape. So this way you need to see that you have some kind of a dead time generation circuit for any gate drive which is having this kind of a top bottom bridge arm in any application.